This second video is going to review dimensional analysis, the process by which we're able to change between units of the same type of measurement, just to represent the quantity maybe in English units as opposed to metric, or from one form of metric to another form of metric. We always start by writing down what's given in our problems, setting up our conversion factor so that if we need one or more than one conversion factor, we make it so that the units we want to get rid of cancel out, and the units that we're trying to find are the ones that are left when all is said and done. We are going to, at that point, solve our problem mathematically by multiplying our numerators together, multiplying our denominators together, and then dividing the two answers. And then we also want to make sure that we apply any sig fig rules as well as rounding. When you're doing dimensional analysis, just changing between units, oftentimes those conversion factors will have unlimited sig figs. They will be based on definitions, exact values. And so if that is the case, only your starting value will have sig figs. If it's something like molar mass, which is based on measurements, then you may have other values that you have to account for when determining your significant figures. So I've given you a chart of metric conversions showing you the relationships between prefixes and the base unit. Grams is used here as an example, but it could be any unit. It could be liters, it could be moles, it could be seconds, it could be not inches. It could be amperes, anything along those lines. Anything above the gray line is a larger prefix, so there are lots of the smaller base unit that would fit into that larger base unit. Anything below the gray line are representing smaller quantities, so lots of them would fit into one of the base unit. And I've given you a mnemonic down there to help you keep track of the prefixes. Some students like to do prefixes always back to the base unit, so they'll have multiple conversion factors based on these equivalent statements. Some students like to just do them in one step by taking the larger prefix and using that to go to the smaller prefix, or vice versa. It does not matter to me how you choose to do it, but if you were asked to solve a problem with dimensional analysis, you need to make sure that you show dimensional analysis as part of your process. So this first one should definitely be reviewed for everybody. 3,800 milligrams is equal to how many grams? We always start again with what we're given, the 3,800 milligrams, set up our conversion factor so that the milligrams are canceled out and the grams are what we're trying to find. Based on that chart I showed you, and you have that in your notes, you'll see that there are 1,000 milligrams for every 1 gram. So the milligrams cancel. We multiply 3,800 by 1, 1,000 by 1, and we get 3,800 over 1,000. That conversion factor is a defined quantity, so it will not have significant figures. But our 3,800 does have sig figs. It has 2 sig figs since those zeros at the end are not significant. There's no decimal. When I divide 3,800 by 1,000, I get 380. So I can't do math today. Sorry, trying to do it in my head. Never a good thing. 3.8. And I do not need to add any zeros because I already have the number of significant figures that I needed in my final answer, which was 2. And I keep grams since that's the unit that I was trying to reach. In my second example, you are going between 2 prefixes. Some of you may have used micro before, others of you may not, but it works the same way whether they're prefixes you've used previously or not. We start with what we're given, the 0.00475 deciliters. Both deciliters and microliters have liters in common, and we can use that to convert between them by using 2 conversion factors. The first one going from deciliters to liters, and there's 10 deciliters for every liter. If you look at your chart, the deciliters would then cancel out, and then we can use liters to get to microliters. 1 liter is the same as 1,000,000 microliters. You could also just do a single conversion from deciliters to microliters, which would be 1 deciliter is equal to 10 to the 5th microliters. The difference between the two exponents, -1 minus -6, tells you how many powers of 10 different the smaller quantity is from the larger. Again, it's up to you how you want to set up these dimensional analysis problems. When we multiply the numerators together and we multiply the denominators together, we will not have sig figs with our conversion factors. So if we go back to our starting value, we see that it had 3 sig figs. And when I do the math, I get 475. I'm not about to try to do it again. Y'all saw how bad I was without a calculator in front of me. So 475 microliters, which could also be written as 4.75 times 10 to the second. That has the same number of sig figs as my starting value, so I am good on that front. Our next example is going to be a calculation that we're going to use dimensional analysis to get two forms of that answer. We're told a compact disk has a diameter of 11.8 centimeters, and I want to know the surface area of that disk. If you read a little bit further, I gave you the equation for surface area, pi r squared. I also wanted you to find the surface area in square meters. So we're going to start by finding the surface area of the centimeter disk, since that's the measurement we were provided with. Diameter is 2 times the radius, so we need to divide that in half. Because that 2 is a constant, we would keep 3 sig figs when we divide it in half to get our radius, 5.9. Okay. We're going to take that, square it, and then multiply it by pi. And when we do that, we get 109 centimeters squared. I also wanted to find what it was in meters. So I can use dimensional analysis to do that. You can take centimeters and turn it into meters, and that will take care of one of the square units. And then you can use that same conversion factor a second time to get rid of the other centimeter. Your other option is just to square that conversion factor. Keep in mind that if you do that, you need to make sure you square not just the unit, but also the quantity that's associated with it, both the 1 and the 100. The conversion factors are not going to have any sig figs, or they're going to have unlimited sig figs, so they're not going to impact on your answer. But the 109 has 3 sig figs. That capped of 0 counts, so we want to have 3 sig figs in our answer in meters squared. That will be 0.0109, or in notation form, 1.09 times 10 to the negative second meters squared. We also have an example here with soft drinks. We're going to use two forms of metric units for volume. We're going to use milliliters, and then we're going to use a cubic form of volume. We often measure volumes in lab in graduated cylinders, which are measured in milliliters. But if you know the exact dimensions, you can measure volume using length times width times height oftentimes. So how can we relate milliliters to just the metric unit? 1 milliliter is the equivalent of a centimeter cubed, and 1 liter is the equivalent of 1 decimeter cubed. Those are some conversion factors you're probably going to want to make sure that you write down, because I believe you're going to have some homework examples with those in there. If I'm starting with 1500 milliliters and I want to get to cubic decimeters or cubic meters, okay, then I need to find a way to relate them to one of those two units. And if I look at the bottom, I see that decimeters cubed, one of the ones I'm looking for, is related to liters. So I could use milliliters to help me get liters using my metric chart, and then I could use liters to get decimeters cubed. Once I do that, I can follow what I did in example 3 and convert decimeters cubed into meters cubed. This is just one way you could solve this problem. So if I start with what I know, the 1500 milliliters, and I know that there's 1,000 milliliters for every 1 liter. Now I've got my problem in terms of liters. I know that a liter is the equivalent of a decimeter cubed. You can show that conversion, or if you recognize that they mean the same thing, you can go ahead and interchange it. I do not need to see the 1-to-1 ratio. But that gives me my volume in cubic decimeters. To get it in cubic meters, I would take that 1.5 decimeters cubed, and I would remember that based on my chart, there are 10 decimeters for every 1 meter, or 1 meter cubed, 1 meter quantity cubed over 10 decimeters quantity cubed. However you wish to go about it, you need to make sure you account for all of the decimeters, and that you take 1.5 and divide it by 1,000. Why did I have 2 sig figs in both of those answers? The 1500 that I started with had 2 sig figs in it. There was no decimal with the trailing zeros. The other conversion factors were all based on unlimited sig figs, so they will not impact on my answer. So I want to make sure I keep the 2 sig figs all the way throughout. The final example we're going to look at involves conversions in both a numerator and a denominator. You're told the density of zinc is 7.14 grams per centimeters cubed, and I want to know what the density of zinc would be in milligrams per millimeters cubed, as well as kilograms per decimeters cubed. So I start with what I know, the 7.14 grams per centimeters cubed. I can turn grams per centimeters cubed into milligrams per centimeters cubed. I usually like to take care of the numerator first, but it makes no difference how you want to do it. And then I can take centimeters cubed and convert those into millimeters cubed. So that's just the first problem. We'll come back to the second one. If I start with my 7.14 grams per centimeters cubed and I use my metric chart, I see that for every gram there's 1,000 milligrams. And that for every centimeter there are 10 millimeters. Okay, so there's my milligrams per centimeters cubed. So because centi and milli are off by a power of 10, I would need 3 of those, or I would need to cube one of those conversion factors, both the number and the unit. Notice that I want to make sure the centimeters cancels out, so I have centimeters now in the numerator so that the millimeters stays in the denominator. All the centimeter cubes cancel out. I'm going to take that 7,140 milligrams and divide it by 10 cubed. And that ends up being exactly the same answer that I started with, because I had conversions occurring. And if you take a look, you'll see the numerator was multiplied by 1,000, the denominator was multiplied by 1,000. So that's why you got the same value, although the units were changed. The conversion factors have an unlimited number of sig figs, so only the 7.14 would impact on the sig figs for my final answer. I can follow the same kind of process to do kilograms per decimeters cubed. I can use the grams to get to kilograms, and then the centimeters cubed to get to decimeters cubed. There are 1,000 grams for every 1 kilogram. Again, only the 7.14 has sig figs, so when I divide it, I would get 0.00714, or 7.14 times 10 to the negative third, kilograms per centimeters cubed. We know that there are 10 centimeters for every decimeter, that there's 10 pennies and a dime. So if we do that 3 times, or cube one of those 3, we will get our centimeters cubed converted into decimeters cubed. And just like in the previous problem, we see that the denominator was divided by 1,000 and the numerator was multiplied by 1,000. So because 1,000 over 1,000 cancels out, we still have the same value with a different set of units. So units play a role in determining what those numbers are. You really want to make sure that you are taking your units seriously and setting up your conversions so that the right quantities go with the right units.